Okay, so today we're going to talk about corner lot, 19th century corner lot buildings. And this was an obscure population of buildings that we've been kind of keeping an eye on for the last couple of years. And weren't really focusing on that much, but we started getting a few incidents and accidents and one-time catastrophic collapses in these buildings. And I started to do a bit of research on these 19th century unreinforced corner lot buildings. And there is actually a history in the department of losing these buildings, going back at least 16 years that I could find. I'm going to show a few exhibits today. And I want to bring it to your attention because it's advantageous for you guys to know what the department is watching. And that's useful for us to know because we are focusing on these things. If we're focusing on them, it means you should be focusing on them. Incidents and accidents in corner lot buildings, and I'll get to how these things occur and why they're occurring and how they're getting missed. It's nuanced. The engineering is difficult. A lot of this stuff is overlooked. We have existing buildings that are fatigued. They're tenement buildings. So there's all types of interesting things going on in these properties that I'll share with you today. But it is not, you need to be careful if you're working around, inside, or next to one of these buildings because they can perform badly very fast. And we lost like 2 of them last year where uncontrolled collapses of these properties caused a lot of fuss. Fortunately, nobody got hurt. But we've had 1 or 2 of these over the last 16 years where we did have a couple of fatalities. And it took me a while to dig them out because nobody was really tracking them as corner lot buildings or end wall buildings. Okay, so the course description. The course description, I'm going to revisit this course description a little bit when I get further into the presentation. You can do a presentation. The building department provides presentations on 2 types of topics. They do statutory presentations and they do educational presentations. Statutory presentations is all about the codes and how the codes are applied to buildings and new buildings. Doing statutory presentations about how a building code applies to a new building is relatively straightforward. But doing a statutory code requirements for an existing building is not so easy. Because a lot of these buildings actually had statutory requirements in the 19th century, in the 1800s, that were not engineering specific. They actually established building geometry. So they did have codes that set up these buildings, but a lot of the codes actually locked into geometry of the building. And the interesting thing about that is, if you run the engineering numbers, which were very scarce at the time, the engineering calculations for these things were pretty well known, but the engineering evaluations and the material science was quite weak at the time. So to circumvent that, a lot of the codes gave you these very high factors of safety in these projects, these buildings. They built them by the thousands, and they established architectural and structural geometry. And that's not the way we design buildings today. We pretty much engineer the components, and the components based on stresses and deformation gives you the structural sizes and where the structure has to be. That's not the way these buildings were done. These buildings, the actual geometry and the architecture and the structure was established in the code through minimum standards. Now, the snag with these buildings is because you have this lack of compatibility between the geometry of the building and the engineering, these buildings last for an inordinately long period of time. Because what happens is they were quite well they were overbuilt. And they were overbuilt for a reason, because a lot of those early codes were established by the fire department. And the fire department were watching for one-time instantaneous collapse of a building that killed people. That was their big objective. It used to be a statement in the code, one-time catastrophic collapse of a building will have to be avoided. Now, we've sort of engineered out this issue, but that's how the code stated way back in the 1800s, especially in the early 1800s. They were watching for buildings that had a one-time catastrophic collapse that killed people. It's a different mission statement from the code now. And then what happened is fire said, okay, well, we like that, but we're going to overbuild the building because we don't want them falling on guys when we're fighting fires. And we don't want progressive collapse. If we lose a floor, the whole building ends up on the ground. And that's kind of interesting because that's the failure mechanism we're getting in them now, where we lose a relatively benign component of the building and it causes this catastrophic one-time collapse. And then everybody's standing around scratching their heads. Well, how could that relatively benign structural event have occurred and brought an entire building down? So we're going to go through that a little bit, okay? There's 13,000 of these left in the city. So the advantage of going through the building department is we do have numbers, and these numbers are hard to get. Many presentations focus on statutory requirements, which is really building specific. But a lot of these existing building presentations, I'm going to give you numbers. Watch out for the numbers, because if there's numbers of these existing buildings and you know where they are and we're watching them, they're going to pop up on your site. And it's good that you're focusing on these things because you may overlook something that could bring a one-time catastrophic collapse of a building down. Okay, if a building collapses and it's empty and we're not that worried, you know, that's a problem. But it's more of an issue when people get injured and when we have fatalities. Those events lead to major changes in the building code. And it's not a material science issue. That's an event-driven change of the building code. Okay, so the other issue is about corner lot buildings is they usually border an avenue and a street, and they have 3 exposed walls. 3 exposed walls, which is unusual. They have 3 exposed walls. So one out of every 10 buildings that were built in the 1800s was a corner lot building, 1 out of 10. Okay, so we have gross numbers. So we're going to get that information to you, and then we're going to tell you a little bit how to keep an eye on these things. They turn up in every borough in the city, but they're mostly in the older, dense urban areas, which means they're heavily trafficked, and they usually have ground floor retail space. Most people on this presentation know that retail space in the ground floor is the biggest generation of income in a building. In the 19th century, that was also the case. So what they had is they had open floors for commercial, for food, and for provisioning for grocery stores. So that's another kicker that goes with these. 3 exposed walls, a geometry built building code from the 1800s, non-compatibility with engineering. So the engineers have trouble engineering these things when they get in existing buildings. You have 150 years of fatigue and deformation in these things. And then you have high public trafficked area along the avenues and sidewalks, and 3 exposed spaces, and a soft story on the ground floor. So we're going to go through the next one. Wear and tear issues. We're going to talk a little bit about that. We're going to talk about the building sitting basically on a soft story. The upper floors, we're watching these ones that are around 4 or 5 stories. That's typically the configuration we're keeping an eye on, where there is 4 stories sitting on a post and beam for the ground floor at the 2nd floor. Cast iron corner column, and virtually no structure on the ground floor. Why? Because a lot of them had shop fronts, windows, and doors to get into the apartments. So there's very little structure on the ground floor in these things. They're soft stories. Okay, so we're going to revisit this as we develop this presentation. We're going to identify where they are and how the structurally sensitive soft story is getting overlooked. Because the issue with the soft story for 19th century buildings, there was virtually no positive connection between the components. The walls and the floors, the cast iron columns and the beams, very poorly detailed and very poorly connected. It all worked in gravity. So I'm going to end up how we ended up here. We'll talk about the structural stability of the upper floors and the unengineered alterations. We'll talk about common engineering and contracting errors and omissions. This is a big issue. The engineers have trouble trying to run numbers in this population. So we're going to talk a little bit about numbers that seem to work that we ended up with. And it's not contemporary calculation methods that we did. We sort of looked at it from a different perspective, and we had a much higher degree of precision of why the buildings are collapsing when we ran some numbers. So we're just going to talk a little bit about engineering and prior code sections that govern these buildings. Okay, you got to remember, we got to watch out for one-time structural events. One-time structural collapses are bad for business. They're rare, but they do occur, and I'll go through a couple of examples. Okay, Most of this building is not, most of these buildings, these 13,000 buildings that we have in here, they're regulated by DOB, but they're generally regulated by HPD because there's a tenancy issue in these buildings. We're also going to talk about the duration of how long these buildings should have lasted. And are we really hitting our numbers for wear and tear? Are they wearing out to a point that they can't be repaired and fixed? We didn't find that, because if you tackle these buildings, you kind of restore them to how they were built. You can pretty much restore the original integrity of these buildings and get those factors of safety back up there. But the downside of rebuilding these buildings is it's prohibitively expensive. And it's very time consuming, and you have to deal with the tenanted group. New York City has regulated tenants, and a lot of regulated tenants are parked in these corner lot, old lot tenements and converted dwellings. So that's another thing that's creeping in here, is you've got these fatigued buildings, hard to engineer, wear and tear materials, soft story on the ground floor, and heavily regulated tenants where they're difficult to move to tenant groups. Okay, and we'll give you a couple of examples of that. Okay. So this statement is important. Full collapses of existing buildings are rare. They are rare, but they do occur. However, partial collapses of exterior walls and floors are frequent occurrences and not so random. We went back through our data. It's a little difficult to data mine the DOB's website, its open data, because when we built these systems, they were just to record alterations in new buildings. They were not really to record for data mining. Data mining is a science that's really strengthened in the last 10 years. When we started BIS 30 years ago, it was not really a data mining exercise. But the information going back 30 years in our BIS system, not so much in DOB now, but in BIS and in HPD, you can data mine it. The other issue is about data mining is you need very powerful computer and analytics tools. And they've only become available in the last couple of years. So what we've been actually doing is we've been writing programs to scrub our open data. We do not scrub private websites. We scrub open data. And now we are getting trends, and we're able to do some analytics and this stuff, which is difficult to do because those heavy websites and those heavy open data sites were not built for data mining. They were just built as a repository of information and complaints. Okay, so we're going to show a little bit about the 19th century buildings. There's 800,000 occupied buildings in New York City, 800,000. New York City has 1.1 million buildings, but there's 800,000 of them are occupied. The vast majority of them are 1 and 2 family dwellings. So we're going to look at that a little bit. But tucked inside these 800,000 buildings is 13,000 corner lot buildings. Now, not every building is a problem, but the ones that are a problem we're going to share with you today. And the classification for these ones that were turning up that need attention and need some consideration. Again, it didn't turn up in DOB's website. When we scrubbed this data, all of this information turned up in our colleagues in HPD's website. And HPD does not data mine. They sort of take a lot of information about tenancy and not much else. But those buildings were actually parked all the way back to the 1800s in another website, in HPD's website. And the great thing about that website is they classified the buildings. And once you got a classification for the buildings, you had an architectural geometry that went with them. It dated the buildings and it gave you an architectural geometry. Then you can match that up with some of the engineering stuff that we have in other websites. Okay, so here's the snag. Corner lot and end wall tenements. They're kind of the same. People don't think that. You have a freestanding building, or a building that's been cut free of the neighbor. You know what that is? It turns it into a kind of a corner lot building. And that's useful for us. So we're thinking now, corner lots and end wall buildings, they have a lot of performance issues that are very, very compatible. And a lot of them turn up in construction sites. Not only are you altering these buildings that require work and understanding, what happens is they're turning up on construction sites where the neighboring building on the other side's been cut free. And we're going to talk a little bit about things that make these buildings particularly tender and require attention, okay? They have high pedestrian on the streets and avenues, so watch that. These buildings, if we have an incident, an accident, it's very disruptive. It knocks out mass transit, it knocks out a main artery through the city, and it knocks out the streets, which is where most of the residences are. So you can get a double and triple-headed problem if you have a structural stability issue with one of these. The other issue is you've got regulated tenants in there, And that is, with this administration, de Blasio's administration, residency and occupied tenancy buildings is a very high priority. There's not much appetite for vacates of regulated tenant groups. We have told landlords, okay, so the buildings got messed up, you did this, that, and the other, and you have to move the tenants. He said, well, they'll move themselves. I said, no, that's not working anymore. You're going to have to put them up in a hotel. And that dialogue is an unbelievable dialogue with the landlords, because after a couple of months, this work is slow to repair. It's slow to get it engineered. It's slow to stabilize. Next thing, you're looking at tenancy groups that are stuck in hotels for months. And that's not uncommon. We had a tenant group in a collapse I'm going to show you. They were stuck in hotels for 6 months. It sounds kind of glamorous that all these tenants have moved into hotels, but they don't have access to their clothes. They don't have access to a kitchen. They don't have access to their home. It's not the same. It's kind of nice for a couple of days, but for 6 months tenancy living in a hotel, it's very transient. It's also prohibitively expensive for the landlord as well. So that's been a big issue as well. These ground floor soft stories, they have large storefront windows and unrestrained bearing walls. We're going to get a little bit to that in a minute. Okay. So what are the big hits on these buildings? Loose and failed cornices. These buildings are approaching 150 years old. Maintenance, maybe not so much. Wear and tear, significant, because the buildings have been occupied for 150 years. Ground floor tenants that move every couple of years. Wear and tear issues, landlords not maintaining the properties, and just general degradation of building components. So we're going to explain a little bit about why these buildings have survived so long in the city for 150 years. I'm amazed by that myself, because if you design a contemporary building, I talked to an engineer this morning, I used to be a design engineer myself before I came over to the building department. If you tell a landlord or a developer, I'm going to design your building, it's going to last 150 years, they're not interested in that. They want a minimum standard building, and the structural stability of that building is good for about 25 to 50 years. Minimum standard buildings are 25 to 50 years before you have to start tackling them and doing some major repairs. That's a long duration for a landlord to have. Most landlords are in it for the short term. They do not look at a building in their portfolio for 50 years. These buildings, 150 years, multiple ownerships, change in tenancy, high occupancy, fatigued materials, no repair campaigns. So we lose cornices on these things to the top of the walls. We lose them pretty frequently. Out of plane masonry, when these buildings start to deform, and they do deform, they relax into shapes. That is a critical issue, and it's always overlooked. So when we see these buildings with bent and out of plane walls and they're leaning 18 inches, the engineer said, well, I don't know why that thing is leaning 18 inches. It's there, it should be there. But that's actually not quite true, because they weren't designed to lean 18 inches. What ended up happening is that the original specifications, the original geometry, took into account these enormous factors of safety. And you have these redundant structural systems inside the building that are all kicking in to make these things basically tenuously stable. So we're going to talk about that. Unrestrained cast iron corners at the columns and steel beams at second floor. That's critical. This second floor soft story issue is critical. We have this issue when a car hits the building. We have it when there's a developer working on the other side and the building settles. It does all types of crazy stuff to the soft stories. Deteriorated and unrestrained stone lintels. We're going to talk a little bit about that. Negative impact to the building from adjacent demolition. That's what a lot of people are here to talk about. It's covered very well in other presentations. But today I'm going to talk about the main things in the buildings that make these things tender, and they perform not so well in the most unexpected manner and ruins your day. Okay, so let's see what we've got. What do we mean by a 19th century unenforced masonry building? Generally between 1814 and 1901. They're typically have been around since 1850. I'm amazed that these buildings are still here. 13,000 of them we counted, myself and my colleague. We found 13,000 of these things. Now, admittedly, there's 800,000 buildings in the city, but to have 13,000 buildings that are on a corner, that haven't been changed, that haven't been significantly rebuilt since 1850 is a remarkable number. Okay, prescriptively designed. So we're going to talk a little bit about they're prescriptively designed. They were engineered but they weren't really engineered like they were for the fire department. Most of the specifications of these buildings and the building geometry and the structural components were actually specified by the fire department. Why? Because they were trying to avoid a one-time catastrophic collapse, loss of a floor bringing down a building, loss of a buckle in the wall due to a fire next door bringing down a building. So what they did is they imposed progressive collapse abatement campaigns inside these buildings. And what ends up happening is we think they're engineering systems, but they're actually not. They were progressive collapse mechanisms. They're nearly all in downtown areas and dense urban environments. Nearly all in downtown areas. So that means there's a lot of foot traffic in there. So we got to keep an eye on that. A lot of foot traffic, avenues and streets, very detrimental if we have to work on one of these buildings with the foot traffic. They're also in high traffic areas for mass transit. We're stabilizing one of these in Brooklyn right now on Smith Street. We built the shed. Con Ed turns around to us the other day and says that one of the shed poles is in the way of their exit into the transformer vault. Required the owner to have to restructure the shed. Very expensive, and a lot of these downtown areas are heavily trafficked with mass transit. We're generally under 4 stories. So this is a kind of a good slide. Under 4 stories, downtown areas, prescriptively designed, typically dating from the 1850s, 3 exposed walls to the elements. That's a big one. 3 walls of these buildings are exposed to the elements. And they're unrestrained, means they're not locked in by the neighbors, which is an issue. They're not locked in by the neighbors. A lot of these 19th century buildings, they get their stability from party wall construction, where the neighbors are helping to hold them up. Now, they weren't designed to be done like that, but now that's how they're kind of working. Okay, ground floor structures comprise cast iron corner columns. Okay, we got that one. And the other big one is that a lot of people overlook. The second floor transfers all the partitions and the upper floors. That's a snag. The second floor transfers the upper floors. So we have a transfer floor on 2, and that gets overlooked. Okay, so let's have a look at these. The typical image. I'm sure everybody finds they're familiar with this. I took these photographs the other day. That's one that I can't. That's down in it's down on Mercer Street. Was that Mercer? It was Grand and West Broadway. Cross soft story on the ground floor. Corner column. Virtually nothing else holding this building up. Couple of cast iron columns. A beam at 2. Heavy masonry above there, and all the second floor apartments. The photograph on the left, there's 2 soft stories on this. This I took around the corner, around the corner from DOB. 2 soft stories. So we have something move around here. We lose these 2 floors of this building. Very common. Okay, so let's have a look at a couple of soft story collapses. Very dramatic. We had this in Brooklyn last year, and it really started us looking, well, really, is this an aberrant condition? Does it happen occasionally? Is it unusual that this thing happens? Did somebody screw it up? So what actually the real snag with this building is, and we really didn't have any injuries, thank God, is that we had a one-time catastrophic collapse of an unrestrained street wall. We had a buckle of that street wall, and it took the entire building down. Now, this is not so good for anybody, because the snag with that is there's very few pockets in these progressively collapsed buildings. So if we did have people inside these buildings, it's very rare that they'll survive, because we have these like floor by floor collapse conditions, which is a real issue. Okay, so the entire building lands in a pile on the ground floor. Very bad for us. So this is what happened is we said, okay, so let's look at a couple of these and see, is it a trend that we're missing? Is there an engineering component to this? What are we missing? Why did this standing building let loose? Well, there was a history of non-compliance down there, and it was quite critical. So, and that got overlooked. And then the other issue is it started us to look, well, how many of these have we had? Is it an aberrant condition, the soft story? So let's actually look at some numbers. About a month after that collapse, we had a second one of these go. And this was in Midtown. Now, it's not quite a corner lot building, but it was made into a corner lot building when the developer working to the west on that site took down all the remnant buildings on the lot and left almost a freestanding townhouse. That freestanding townhouse had been altered significantly over the years. And then what made the situation worse is there was some underpinning that was done underneath that and some foundation work. and you had this one-time catastrophic collapse, very detrimental. The real snag with this, even though nobody was injured, which was good, it caused the site to be shut down for 6 months, and it caused the vacated the corner lot building next door, and that building became unstable. And that was a real issue because all of those tenants had to be put up in a hotel. So again, you're seeing something develop here. Okay, now I've got to keep an eye on these things. Why? Because it's painfully difficult to sort it out once these buildings get away from you. Then I went back in time to look at a couple of other collapses that I'd worked on over the years. This was one that we had in Carroll Gardens in Brooklyn. What happened on this particular one was the neighboring building was cut free in the 60s to put a school in. What it did is it left an unrestrained party wall. Party walls should have been tied to the floor joists, except when developers were putting adjacent buildings next to each other contiguously, they had the floor joists from the two adjacent buildings locking in the party wall. So this wall actually never got any mechanical ties other than the fact that there was joists on both sides of it. Now, it took this 60 years to decay, but when that went, it went unexpectedly, and the building was full of people. Nobody got injured in that building because what stopped the floors from collapsing in it was the relieving walls. The relieving walls around the stairwell were actually another progressive collapse mechanism that was imposed on buildings that was a geometric and an architectural layout that the fire department put in existing buildings that says, even if a bearing wall lets loose, we want a third bearing wall in the building to stop progressive collapse. And that's why that building didn't collapse, because the floors got hung up off the stairwell wall, which is great. Look at that. All the floors got hung up on the stairwell wall, and we lost the entire bearing wall. But that's not the case in the corner lot building, because the relieving walls do not go through the retail space. And that's why we have such sensitivity in an entire building collapse in a corner lot mixed-use buildings, because the relieving walls do not go through and act as a third bearing wall. And that's a significant structural difference here. So you got to keep an eye on these end walls where the buildings are left as a remnant structure on a terrace, that the relieving walls, and then you don't have a soft story inside there where somebody's cut a relieving wall free. That means that that bearing wall, if it performs badly and buckles, you lose the entire building. If you lose the entire building, anybody who's in there will, we won't be able to have trouble getting them out. So then what I did is I went back and I looked at a couple of other collapses that we had. This was a collapse we had on West 123rd Street. Spontaneous collapse, out of the blue. The building was empty. The developer was going to renovate it. The owner was going to renovate it. But that building went on its own, and the condition on the right-hand side is exactly the way I found the building when I went up there. It entirely collapsed. Why? It was cut free of the two neighboring properties. It's quite narrow, so the aspect ratio is kind of slender, and none of the walls were tied to the floors. Why? Because all of the row houses were all built contiguously, and the floor joists were locking in the relieving walls, and the developers just took a shortcut and didn't put the mechanical steel ties, which were in the code, to tie the walls to the floor. They were never put in there. Very dramatic failure. Nobody was injured, no collateral damage, nothing. The attribution from the developer was that the electrical cable that was on one of the building walls pulled the building over. So that's what their attribution was. Nobody was injured. It was pretty dramatic, but it got overlooked. So this was one of our problems. When we have these no injury job sites, we don't spend as much attention on them as we really should, because what it does is it tells you if you start looking for them, you find others. And that's advantageous in some of the data mining that we've done, because that collapse was parked in my data, but it was never made into any global data to say, keep an eye on this type of structure, a freestanding row house, unrestrained, where the conditions are decaying. Okay, next, this was a building that we had on 125th Street. I'm showing you this because it was actually a demo that was underway. It was a soft story tenement on a corner where the developer and the demo guy had elected, they were contracted to do mechanical demo for some aspects and hand demo the building. And the demo contractor decided to take a shortcut and take the building down with a backhoe. And what ended up happening is the soft story collapsed, and it brought down a mercantile and it brought down the tenement onto a bus, and there was 18 injuries in that bus. Okay, so that was a mechanical demo done of a soft story building. These are frail. When you're taking them apart, you have to make sure that you have a stability issue. The contractor had very little regard for the safety and welfare of the public. The demo contractor was reckless, and this building predictably collapsed into the street and landed on a bus. So that was a big mess. So that was another one that was hidden in our details and hidden in our data. So I dug that out. I only dug that out last week. I think that was 2012, that one. And here's another one. This was a very dramatic collapse that we had in 2008. We were walking up to the building after a report from a geotech engineer who was working on a new building next door, said that the building seems to be cracking and moving. This remnant old law tenement that had a soft story where the collapse was, had a retail space, had a cast iron column. The developer who was beginning to work on the site next door undermined the cast iron column. And they were messing up the site and getting it ready and doing supportive excavation. In the meantime, the soft story, which was extremely frail, had quite a lot of damage. The building was vacant. That remnant building was vacant. It was supposed to be renovated by the owner. There was regulated tenants in there. There was all types of shenanigans with the structure and the owner. And then all of a sudden, as we were walking to the building collapsed. Again, the same characteristics. And, you know, this is another one that we kind of had hidden in our data. And I dug it out and I said, so there's quite a lot of patterning to this, which is useful for us to know. These collapses go with patterns, and the maintenance of the building go with patterns. And we're going to share that a little bit with you. Why? Because we would like to talk about statutory requirements in the building code, but the statutory requirements for the maintenance of this building is frankly, it's quite soft, because the original code that you have to daisy chain back with was not an engineering code. What it was an architectural and structural geometry code. This is how the buildings are to be built. It was an actual architectural code built by fire department. Very little in there about allowable stresses, loads on the floors, material properties, virtually nothing. It gave the geometry of the building and then said, by the way, this building has to have a factor of safety of 6. And by the way, don't forget to put a relieving wall stop for progressive collapse. That was the inference in the commentary. Your presentation today is educational. Why? Because I'd love to hang on to some statutory requirements for existing buildings. The problem is they're quite weak. We're working on an existing building code to take care of that. The new building code, new buildings, it's all, the presentations are statutory. This particular presentation is statutory, but it's mostly educational. Okay, so failure of a wood, so let's just talk about things that fall in these buildings, okay? Failure of a 140-year-old wood cornice. It's very common, but it lands on the street. And when it lands on the street, it's dangerous. They're easy to take off and restore, straightforward work, but it's expensive. Okay, so taking the buildings apart, taking components apart, very easy to do, replace them in kind. Good luck trying to make any of that stuff work engineering-wise. You end up with crazy engineering when you try to restore these things in kind. Restoring them in kind restores the building to a factor of safety of 6, and that building was good for 150 years, but it makes it very difficult to make it compatible with an engineered building. I'll get to that in a minute. Here's another one that you have to watch. Separation of an exterior wall pulls the floor joists free of the wall. And the other thing about these buildings is, in the architectural codes of the time, they refer to architectural brick laid on the outside of these buildings. These red, square, 8-inch running bond bricks, they're called Philadelphia Press bricks, was in the codes in the 1850s. They were laid up in a running bond pattern for architectural reasons, referenced in the code, and supposed to be tied to the backup brick every 6 courses. Rarely done, rarely done. So what happens is that architectural red brick that you see all over Brooklyn, you see it all over the West Village, you see it down here all the time, running bond, exterior brick, tuck pointed 1/8 of an inch mortar joints, very nice brick, big long brick. These things delaminate from the backup wall. They peel away in sheets. And it's very common for the architect and engineer. What happens is, it happened to us in Brooklyn recently, where they thought that architectural brick was actually it didn't contribute to the structural stability of the wall. Well, actually it did. It was 4 inches of a 12-inch wall, and it had delaminated, and they thought, well, it's okay, the 8-inch wall is going to carry it. Problem with the 8-inch wall, it was buckled out of plane, and that didn't work no matter what way you looked at it. The 8-inch remnant wall was actually out of plane, and it had a big buckle in it as well. So the outside wall, the 4-inch running bond brick delaminated, came away in sheets. The 8-inch wall was now out of gas because there was a buckle in it, and there was loads of windows, and it wasn't laid up very well. And then what happened is the entire wall gave out in one shot. And the rate of decay of this stuff is slow. The rate of decay is over 150 years. So it's not perceptible to the eye. So every time somebody walks down there, they say, well, I saw that buckle 2 years ago, and it doesn't look like it's actually getting any worse. What actually has happened is it's taken 150 years to buckle, and the rate of decay is slow, but it is absolutely moving. And the issue is, when these things are moving, you get buckles, and when they buckle, they go instantaneously because it reaches its threshold numbers where the factor of safety is lower than 1. It was built with a factor of safety of 6, so how in God's name can a building with a factor of safety of 6 collapse? Well, it collapses because of decay of the material. It also collapses because of buckles of the wall. End wall and corner lot buildings are unrestrained on 3 sides, which means they're free to move. The other issue about these buildings is they were allowed to deform when they were built, and I'll talk a little bit about that. Taking them apart and putting them back together again is relatively straightforward work. The only problem with it is you have to shore the inside, which means you got to move the tenants, and that means you got to move a commercial tenant and usually 4 tenant groups inside the building. They're regulated. It becomes almost impossible to move these guys. Then you have to shore the building, and then you got to take it apart and put it back together again. Prohibitively expensive for a landlord that has regulated tenants and a ground floor. You'll find that that's going to be their biggest complaint. They don't get an insurance claim because it's a failure to maintain issue, and then the repairs themselves are prohibitively expensive. So we'll get to that. Can you take them apart and repair them? You absolutely can. But if you run the numbers, they're not compatible with a factor of safety of 6. They actually end up with a lot higher factor of safety than that. A lot higher, because fire department said we don't want progressive collapse. So what they did is the interior relieving walls were third bearing walls, and they actually take load. What's the problem with that? The load is discontinuous at the 2nd floor over a mixed-use building. So then you have this soft story issue. So the front to back stairwell walls, you can also repair those things. The biggest decay we get in these things, 2nd floors. You look at the 2nd floors, they are absolutely out of gas because they are taking all the interior semi-load bearing partitions. You have the wear and tear from bathrooms and fixtures and fittings, and you get these enormous deformations on the 2nd floor. So the 2nd floor is usually fatigued. You get buckling in the outside wall, and you have a soft story on the ground floor. One of these elements lets loose, you will have a progressive collapse inside this soft story building. Okay, moving right on. So here's one that we had 2 or 3 weeks ago, where a car went into a corner lot building. Is there anything unusual about this? No, we have this on a regular basis. It's very dramatic. When a car strikes a cast iron column, that cast iron is brittle. It fractures. When it fractures, it's done. Steel bends and will deform when it's impacted. It does not have a brittle failure factor on it. Cast iron will actually fail in one shot. So you got to watch that. The other issue about cast iron is the connections between the overhead structure. The beams were gravity connections. There was hardly any bolts in there. So you can lose a corner of a cast iron building, and it's a real issue because the overhead structure is all bearing on the beams. This particular one was a relatively small building. Car struck the column, broke the column, and we were able to get in there, have the building shored, and it's actually, the building is needle beamed right now. Retail space is gone. It was a pharmacy. They're out. And the 3 overhead tenants, which were regulated tenants, are out. Now, the landlord is trying to deal with the tenant groups because of these, the tenant advocacy groups in New York City. So they're stuck with a repair campaign that's going to go at least 6 months. And these displaced tenants are out for 6 months. Plus the commercial guy on the ground floor. These are tenant groups and commercial spaces that we want in neighborhoods. They are important retail spaces, they're grocery stores, they're local pharmacies, they're food provisioning. It's not a Whole Foods. These are not Whole Foods. They're not, these big retail stores. It's not Macy's. These are mom and pop shops that are reliant on their business. They got 2 or 3 people working in there, and you've got these minimum standard apartments that are, they're not on the higher end of the rental incomes either. So we want all of these guys in there, and 13,000 of these buildings, it's too much to take on to have them all taken down and rebuilt and everything. It's just not going to happen. So we try and restore these buildings as best they can, because it restores the tenancy, it restores the retail space. It's all good for everybody. Okay, so we short and brace the building. We had it needle beamed, and they're putting a white flange column in there, a column section instead of the cast iron. But man, when that guy hit that column, it snapped it in half. So very typical. And of course, the driver survived, and there was no injury to the driver, but he took out this entire building. And fortunately, nobody in the pharmacy was hurt. Okay, so this was a building that I'm going to show you a photograph of this in a minute. When you take these buildings down, it's amazing what you see on the other side of the party wall. There's 3 beams, that are sitting on a cast iron column for a corner lot building that was an 1830s corner lot building. We're just taking it down in the West Village right now. The buckle, it was an 8-inch bearing wall. It had pulled 4 inches free of the joist. When I got in there, none of the joists were connected to the bearing wall. What was holding up the floors, I could not understand. Soft story. What ends up happening is you get this diaphragm action in the floor where it actually hangs. Basically, it hangs from the 3rd floor and the 4th floor. All the joists start to hang. There was no bearing walls inside that ground floor. And we put some shores in there just to stop it collapsing when we took it down. But the bearing walls were 8 inches. Okay, they were 8 inches, and it was an 8-inch bearing wall. It was a massive buckle in the wall, and the joists had separated 4 inches. The engineer who was asked to evaluate the building never picked it up. A reputable engineer. The buckle in the wall was not restrained. There was no lateral bracing put on it. There was no effort to shore and brace the building. And the landlord had been campaigning to take this building down for decades. We lost a tenant group. We lost the ground floor tenant. It was a landmark building, so that's gone too. And it's in a very picturesque part of a landmark neighborhood in the West Village. And so what happens is you take this building down and reveals this ghastly situation for the remnant building next door. Big gravity beams sitting on a gravity connection on a gravity cast iron column. Everything was laid up plumb straight and true in these original buildings. But now as walls buckle and everything, you get this big cascading effect where stability is at risk. Okay, component failures. Component failures, we have them a lot as well. Component failures, we have collapses of cornices. When the cornice pulls away, we lose that outside 4 inches of brick of these running bond walls. Very typical. See that photograph? We have it all the time. So the issue is now, how do you rebuild that wall? Do you have to take off that 4 inches of brick, which is peeling away from it? Do you restore the cornice? Do you move the tenants? Do you shore and brace the building? And the answer is you have to do all of the above. And of course, the landlord has regulated tenants, so he has no interest, no motivation to do any of this work. The regulated tenant group, he said, let's take the building down. I'd rather take it down. I said, that's not going to happen. You take that building down, you're going to have to rebuild it. One is in the landmark district, which means we're going to get you for the fair market value of the building. And then you've got all the tenant groups advocating for the regulated tenants. The restoration was done and we reshored and braced the building, but it went, it was a lot of work with the landlord. Okay, and it took a long time, it took 6 months. Okay, deformations in these 19th century buildings. I'm always amazed that these buildings can deform. That is a building that is around the corner from 280 Broadway. It is a little federal era townhouse. It's a corner lot building. These buildings were not built to sustain stiff construction. They were allowed to deform. Why were they allowed to deform? Because they had very high factors of safety for progressive collapse. The rooms were small. If you had deformation in the floor joists, it didn't really matter because the rooms were only 8 or 10 feet wide. So therefore, if you had a sloping floor, you didn't notice it in 8 or 10 feet. The only time you noted big deformations in these buildings is when they removed the relieving walls and get rid of all the bedrooms. And then you say, oh my God, look at the size of the pudding bowl in this room. The deformation in these buildings is outstanding. I've seen these things 18 inches out of plane. Why are they still stable? Because deformation, and these buildings are extremely plastic. They're not elastic, so they don't conform with elastic theory. They do not rebound. They do not recoil. They do not recover to their original shape. They deform and they redistribute the stresses. How could that be? Because they were built with these enormous factors of safety. The code allowed factors of safety in these walls of 6 and 8 to 1, 6 to 1, which means that as the buildings deformed, the load got shed to another area that could take it. And the other issue is, in reality, the loads are not realistic anyway. If you look at the amount of material on the loads, contemporary loads on those floors, they're not as loaded as one would imagine. So therefore, these overstress conditions that you get when running engineering, elastic theory, they don't conform to these buildings. And then all the engineers say, none of the engineering calculations work. And I say, well, that's actually not true. For a start, you're dealing with a plastic building, and these conditions are plastic deformation issues. And it's a plastic theory type issue as opposed to elastic theory. So the deformations, you can discount it, but forces you into just using the stress calculation. Stress calculations, you have some chance now using stress calculations. But as soon as you try and run the deformation calculations, nothing works. Why? These buildings were built to deform, and they're soft buildings. Therefore, they correct themselves. As the buildings deform, they correct themselves without losing an enormous amount of strength. It always surprised me that these buildings will correct themselves. Look at the shape of that masonry on the. It's plastic. It's almost plastic. The way the building deformed 6 to 8 inches, and you can hardly see any cracking in the masonry. Okay, so here's another component failure. Hoods, brownstone, trim on the front of these buildings are constantly falling off. Why? Water gets in behind them. They were never tied adequately. And then we get this dialogue that says, how could this thing fall off the building? There was no mechanical ties. And I say, well, that's actually not quite true. For a start, you've got a building that's 150 years old. 150 years old. You've got decay of material. It's just moving very, very slowly. You have deformation in the building. And there's evidence that there's been a structural problem on this condition for 20 and 30 years. So how do I know that? Because the floors are deformed, the brownstone is cracked, you got buckles in the wall, and you missed your window to try and get in there and take this thing apart and put it back together again. Now something falls off and everybody's surprised. This is not quite a surprise to us. The owner now is in a situation where you have to restore these conditions, take the building apart, move the tenant groups. Nothing is planned, and all the bills come in at once. You can't plan your cash flow for these buildings over a couple of years. When these unsafe conditions hit, you get bills the following day. It's a big complaint from these landlords. I have these huge bills from my engineer and I don't have the money to pay for them. If you plan the repairs in advance and the restoration of the building back to try and reinstate these things, you can do it over 2 years. It's done in facade repair jobs all the time. You plan the work out 2 years and you fund it over 2 years. Okay, and then you don't have the same drama with tenant groups. Some tenants are leaving anyway. Some tenants, you can move them if they have time. Some tenants are going to be away for the summer. They will work with landlords, but you got to give people time and notice. You can't wait for the brownstone hood over one of these front doors to fall over and land on the street. That particular building, all the hoods were missing. The hoods were missing. That was actually in Brooklyn. The brownstone hoods over all the windows were gone, which means that this building had already gone through one trauma and all the decorative elements were removed, and it was a stucco job, leaving the hood over the front door. And then that got modified, and it was in bits to start with. So the fact that it fell on the street and didn't kill anybody was amazing. Okay, so we're lucky. Can you shore these buildings? Can you repair them? Can you put them back together? The answer is yes. They can be demolished and reconstructed in kind. This is a building we did on Clinton Street. There was a lot of regulated units in here. And we were in a position where this buckled, like it was buckled 14 inches out of plane. The joists had pulled free. It was in precipitously close to failure when we got there. Somebody called it in. I don't remember who called it in. I think it was one of the engineers that was asked to evaluate called it in. And they said that the joist had pulled free. So we went down there. The first thing we did is ordered a shoring and bracing job. The landlord for this particular building actually outlaid a lot of money. They had enough housing stock to relocate the tenants. The tenants ended up going back in, but the wall, that end wall, that corner lot end wall had pulled 8 inches free of the wall. Now the snag with that is you've got a floor now that's been held up with the stairwell walls. So people think it's structurally stable. It's actually not. What's happened with the building is it's hitching a ride off the stairwell walls, which were originally put into the buildings to stop progressive collapse. And that gave everybody a false sense of security that the building was stable. It actually wasn't stable. So the floors had relieved the load off the wall, of the exterior wall, which had pulled free from them, and had dumped the loads of the floors into the relieving wall around the stairs. What could have happened in this particular building is nobody missed it. Nobody saw it. And then they took a relieving wall out. You would have had the entire building come down in one shot. And that happens with alterations when the architects asked to open up a ground floor. Well, let's open up this ground floor. So what happens is they open up the ground floor and they see all the floors are buckled. And then the next thing is the second floor starts to dish very aggressively. And the outside wall starts to buckle all in one shot. Happens a lot through the alterations. So now you're dealing with an existing building merging with a building code issue where you have a permitted alteration job and somebody's missed this issue. So we're talking to you today about statutory requirements. What we're really doing is educating our community, our engineering community and our building community about these buildings being precipitously close to being a problem. Are they collapsing? They're not collapsing right now, but if you lose one of these things with a relieving wall removed and the outside wall buckles, you've got a lot of material going to come down in one shot. Okay, how many of them is there? 13,000. Have we got an existing building code that addresses this issue? Well, we have statutory requirements that require walls to be tied to joists. They were always required to be tied. Wall thicknesses, engineering, blah, blah, and all the rest of that, but it's a bit vague. Okay, can you take the thing down and put it together? Shore the inside. We had a nice shoring job. Took it apart, put it back up again. Took a year. But we got the tenants back in. But the other issue is the landlord was able to renovate the building. And that was a big plus for him because not all the units were DHCR, were regulated units. And what happened is he was able to get an increase in a market rate apartment that was renovated. And it's a very desirable neighborhood. So there was some financial gain for this building, for this enormous expense of taking the building down, putting it back up again. It was also in the landmark district. That was an 1860s cast iron loft. Now that was a loft. It was never designed to be a residential building, but there is gazillions. There's actually not gazillions. There's 700 of these things in New York City, where they were mercantile lofts from the mid 1800s that were converted to residential use. That particular building, that each unit was really quite large. It was about 1,400 square feet, and it's around the corner from the building department. Each unit was able to cough up a lot of money to rebuild the sidewall of this thing. But that building got short and they rebuilt the side wall. And a lot of the tenants who funded this repair themselves, there was no landlord. Everybody was a landlord. 1, 2, 3, 4, 5 landlords on that building. They all put up 1/5 of the repair, taking the wall down, putting it back up again. They took it down, and that's the way it stands right around the corner from 280 Broadway. The buildings on the right, this was a complicated package that we had in the West Village. We lost one of these through a chimney collapse. And then what happened is the chimney collapse raced across 3 buildings and brought 3 buildings down all at the same time. So it took us almost 5 years to rebuild this package of buildings. The landlord put up the money for these things. There was DHCR units in, there was regulated units. There was one commercial tenant in there in the building on the left. Took 5 years to take them apart. The snag with it was all landmarked in the West Village. And these were cultural and architectural landmarks. So the landlord was stuck with this package of restoration. A very complicated package, but there was some return. When we took them apart, some of the tenants moved and they were able to make market rate tenant groups in there. So there was some return, but it was an enormous amount of work. Taking it down, putting it back together again, there was improvements made in the building, but it was basically a facsimile of what was in there. Okay, this is the building you guys should be familiar with. It's 287 Broadway. It's right across the building. It took us 11 years to get that building sorted out. 11 years. It's a corner lot building. It moved 18 inches when the tower, the residential tower, went in next door to it. The building had a double-depth cellar, and one of the cellars was actually backfilled in the 1870s when the building was converted to a bank. The developer missed it and the engineer missed it. So when they actually did an excavation, they expected to find the foundation, the south foundation wall down at minus 12 feet. Turns out the south foundation wall was actually at minus 19 feet. So they kept on excavating, and when they excavated, the building moved 18 inches. So it was a huge amount of work. The original shoring that was put on that building was actually wood. Horrible, combustible. How it got approved? It got approved. Then we swapped it out to steel, which was non-combustible, which was better. And that building stayed short. And the building at the moment was reframed, and there's all new floors in there. It was just finished since 2007. It was finished about 2 or 3 weeks ago. Lovely job. Reconstruction in kind, absolutely. 18 inches out of plane. How could you even justify 18 inches for a building out of plane? But yet it stood. Why did it stand? Because there was such redundancy in the geometry of the building when it was built. Okay, determining stress. Let's look at a couple of numbers, this is a kind of handy thing now, because when we move into an education presentation, what I did is I looked at some of the numbers. So looking at numbers are hard to get, but we've been at it a while, and this is what we got. 800,000 occupied buildings. There's 500,000 of them are 1 or 2 family dwellings. You can get rid of 1 and 2 family privately owned. They rarely turn up as a problem for us. Rarely fires, rarely fatalities, and they're usually freestanding wood frame building, prescriptively built. So you get rid of those. 140,000 multiple dwellings. These are the ones that are causing us problems. They're basically unreinforced masonry buildings. A lot of them are noggin wall buildings in Brooklyn, which are wood framed. You have 16,000 apartments that are over 6 stories. Get rid of those. And you have 100,000 commercial, public, and others. You can get rid of those. So the buildings that we're chasing is this 140,000. They're densely packed with tenant groups. They're fatigued buildings, generally anywhere from 1815 to 1901, 1929 for the new lot tenements. So then if you add up all of these buildings and you get corner lot buildings, you get 130,000 corner lot buildings in the city, 130. Okay, so that's every corner lot building that's in the private dwellings, the multiple dwellings, the apartments, commercial. We don't need 130,000 corner lot buildings. We want to focus on these ones from 1850 that are old lot tenements, because these are the ones that we found were falling down. Not the ones that are framed and over 7 stories, they don't fall down. 1 and 2 family buildings that are on the corner lot, they don't fall down. Ones that do fall down and have progressive collapse issues, these multiple dwellings that are old lot tenements. The advantage of going back through our records was that's what we got. That was the pattern we found, that we could get rid of all of these. You're not looking at 800,000 buildings. You're looking at 140,000. Now you can data mine there. So this is what we got. Old lot tenements, there's 3,400 of them in the city. That became a problem population. 3,400 is too much for us to take on. 1 and 2, new lot tenements, 7,600. That's a problem population because they have the soft stories, dense urban areas. They don't have as many problems as the old lot tenements, which predate 1901. Most of them are built between 1850 and 1860. But it's a good number. Throw that in the pile. So we threw that in the pile. And converted dwellings, which are really 2 family dwellings over a mixed use. There was 1,700. The other ones, the later buildings, we didn't really care about those. So now we got the number from 130 down to 13,000. 13,000 still too big a number for us. We cannot blanket the city 13,000 buildings. Fire department has assets to look at 13,000 buildings. HPD has assets to look at 13,000 buildings. DOB, we don't. We look at complaints, we look at some compliance, we look at alterations. So what we did is we did a little subgroup, a mock-up, a quick dry run on some of these buildings. We looked for everything with a commercial space on the ground floor. We were able to find those through DOF. DOF is billing the building for commercial on the ground floor. So we pulled those out. We looked for failure to maintain, which is 130 of 73. We pulled that number out. So now we're getting that 13,000 buildings down to a more manageable number, because we're going to go out and we're going to look. So we have to say, okay, to our commissioner, are these things falling down? Are they all falling down? Is there a subcategory falling down? Can you look at this number and figure out which ones are causing us problems? So we said, okay, so let's do a little bit of a check with our own guys. Let's do a couple of 100 buildings. Okay, so how do you pick them? You pick them with the ones that are ground floor. So how do you find the ones with the mixed use on the ground floor? Well, you have to go to somebody else's data. What data do you go to? You go to DOF. So you go to DOF for that mixed use on the ground floor. Where do you find the failure to maintain where people have not been repairing the buildings, but there's a report of failure to maintain? Well, actually, that you get from our complaints. We have 2.5 million complaints going back 30 years. All you have to do is scrub the 13,000. You get rid of everything that doesn't have commercial on the ground floor. So you put that in a separate pile. So you got your number down quite a chunk. Then you run every complaint for failure to maintain where they got a hazardous violation. Now that number is beginning, so we're getting a much targeted population. We're not just indiscriminately saying 13,000 buildings are bad. What we're saying is, okay, let's look at the ones that we have reports of complaints. So we issued the hazardous violations. In other words, we have a complaint for repair, but there's no repair. So what's the point in looking at those? Somebody went and looked at them, thought the building was okay. So let's look at the ones that did get a violation. So we put those in the pile. And then we looked at the biz filings to see if anybody would repair anything. So we went through we scrubbed more data, and we got that population down to around 400. So that was nice. So we got it down to around 400. So we said, okay, what have we got? Buildings that are 4 stories or less? Yes, that's what we had. Buildings on corner lot with failure to maintain? Yep, we got those. Commercial use on the ground floor? Yes, we got those. Are they pre-1900? Yep, looks like we got those too. So what do we do with these 400? Do we do them all in one survey, or do we do them in 2 surveys? We actually broke them down into 2 surveys. It was easier for our inspections to do them in 2 surveys. A little bit of science with this stuff now. It's kind of nice. Total population of 13,000 buildings. Do we need 400? Let's go out and have a look at 400 and then report to our commissioner. We also have data on collapses, partial collapses, and we got that stuff dug out of our data, which was buried for decades in there. So we've got our arms around this thing, and that's why we're doing an educational seminar with you now. We are showing you what we're finding. If we know it, you should know it. So there's no secrets here. I'm going to show you the ones to keep an eye on. Why? Because people are working on these buildings. They don't know that there's an issue. And the engineers are generally not being diligent about checking this stuff. And we'll explain a little bit about that. So we did these 400. We ran them through a spreadsheet, boilerplate Excel spreadsheet, nothing complicated about that. Borough, block or lot, bin numbers, community board. Community boards is a useful data point. Community boards tell you if you're in a dense urban area. And these buildings are primarily on older, first developed, first generation, dense urban areas in the downtown parts of Brooklyn, Queens, and Manhattan. Some parts of the southern Bronx as well. Not so much in Staten Island. So community boards was useful. Number of floors, we ran numbers of floors. Vacate orders, and all of a sudden we found we had vacates in there. Stop work orders, we found that there were stop work orders in these buildings for work. So we started to uncover all of this nasty stuff that's asleep in our database. OT work, was there structural work going on? Yes, in 2018, 2017. So we started looking at this. One thing we found that was complete rubbish was the DOF data construction. And this is what the data construction is. I just put it in on that spreadsheet to show you how far off DOF is and ACRIS is and the city data is on data construction. These buildings all predate 1901. They're by definition old lot tenements and heretofore converted. These are pre-1901 buildings. And yet DOF has them as 1930, 1934. So we get rid of that. But we pulled the information and just have a look. Complaints, we had complaints. Date of inspections. Okay, we got that. Who the inspector was. We tried to keep a couple of subject matter experts on that. And then we had complaint disposition. Oh, that's interesting. So we went there. We went on a blind complaint and we found failure to maintain. Notice of violation issued. Yes. So we said, okay, so we were having a recurrent structural issue. And then we have the notification numbers. Emergency order. Some of these things needed sheds immediately. So we did 400 out of 13,000, and now we have some stats. This stuff is scalable. We can sort of work the numbers up and down, and we're going to share it with you. Otherwise, we wouldn't bother doing this educational and statutory presentation. It was amazing what we actually turned up in the data when we actually did the data scrub. The earliest corner lot building that we found was a building that was built in 1830 by J.J. Astor. And that building actually turned up in the news recently because it was under one ownership since the late 40s. It was built in 1830 by J.J. Astor. It is virtually unaltered, and there's been no repairs. The reason why it's stable is because the spec that went with this building actually had quite a high factor of safety, and it was built as a mercantile by J.J. Astor. It was not built as a residential building, and it has stayed in basically the same use in New York City since 1830. A remarkable thing, legacy building, and it was just sold recently. And I've forgotten what the deal is with this building. It's a landmark building, and but a gorgeous little building, and it turned up in our data. And all of the stuff, oh, by the way, the tenant was in there. The same tenant was in there since the 50s, and they're still selling the same stuff in there, which was basically hosiery, underpants, shirts, vests. Amazing. There's been in there since the early 1900s. Lovely sort of New York story. But look at what we have. Soft story, no commercial, no structure on the ground floor, and it makes it around the corner. So this building has basically nothing on the ground floor holding it up. Soft story, wonderful. Here's another one that popped up in this metric. A landlord had bought this building about 10 years ago. They tried to buy the guy next door and develop the entire block. The guy next door didn't want to sell and wanted to buy the developer out. So what ended up happening is nobody ended up selling anything. So the developer got stuck with this property on the corner, and it has been sitting idle for 10 years with failure to maintain, and this guy is nowhere to be found. He is waiting for a collapse of this building so we can redevelop that corner. And the other issue is he had no cooperation from anybody. I actually knew the engineer that was working on this, and it was remarkable. The engineer, very capable engineer, but the job stalled based on what they planned to do. You know, I'm going to take this building down, I'm going to renovate it, I'm going to enlarge it, and then everything went to hell because he wasn't able to get the adjacent property. And it was interesting because the neighbor had exactly the same situation. They were trying to buy this guy out, and nobody ended up restoring the buildings. But there we have it, an old law tenement, vacant, in very poor structural condition, no renovation work, friable structural, and a recalcitrant owner. So it turned up as it did. So our search is showing that we are finding these buildings, which is useful. Here's another one we found on Lexington Avenue. This building was virtually empty. It was to be redeveloped. Whether it'll be redeveloped now or later, turns out the owner actually owned a bunch of tenements, and they were all contiguous. And he was emptying these buildings over decades. The light you see on the third floor was actually coming from an extension cable that was from the ground floor tenant. So what the landlord did is he emptied everybody. The building was in bits. There were regulated units. He was letting the building decay, not repairing anything. We had recurring failure to maintain issues with this thing. No engineer in sight, yet there's tenants inside the building. How are they doing? After the landlord knocked off the power, the tenant worked out an arrangement to run a cable up from the retail store on the ground floor. And that's why the light was in there. So there was occupied units with no electricity in the building. So, okay, so that was pretty discouraging to find. And it turned up a couple of buildings we're actually working on. So we have a building down in Lower Manhattan. It's a mercantile loft. It was on piles. The piles, it was underpinned recently, but the wall is like 14 inches out of plane. So there's a big tussle going on between the landlord and the tenant groups, the advocacy groups and landmarks, trying to restore this building. And in the meantime, I'm trying to get this thing rebuilt, the sidewall and the building rebuilt. It's possible that it will be rebuilt, but you know, it's a problem. This thing is like 14 inches out of plane. We've tied it together, but you can see, I mean, it's not a great situation, and it's on a heavy thoroughfare. There's a bar beside that. There's commercial on the ground floor, soft story. Okay, so all the stuff. Okay, so what did we find when we looked at 400 buildings? 50% received a class 1 violation. Is that unusual? Well, we actually told the inspectors we do not want frivolous violations issued on this. Do not go out and just write for some administrative issue. I want real evidence of failure to maintain. This is why we picked our inspectors. We picked inspectors that could determine that there was a structural issue so we could get correct data when we data mined after we did the 400 surveys. What we found is 50% of this package of old failure to maintain, old lot tenements, corner lot buildings got violations. And they were class 1 hazardous, so they were serious stuff. 20 were considered structurally compromised. We had to refer them to my other, the other engineering groups, the forensic unit, and it started the dialogue with the owner. So the owner said, well, I don't have any money. My engineer doesn't know what he's doing. The building is, I've got tenant groups, that type of stuff we were able to get under control. In fairness, we ended up taking 1 or 2 buildings down. So that 20 did make it to demos. We ended up doing a bunch of demo packages in here. Buildings that were planned to be demoed, but just the owner did not elect to do them yet. That was bad for us because there was plans to demo. They were just sitting on them, warehousing them. But the buildings were precipitously close to collapse. So what we did is we told the owner, you got to hit the gas on these demos. He said, I'm not quite ready. I don't have anybody to move into the site. I'm going to sell the site. I'm not going to sell the site. So what we did is say, okay, you don't want to take them down, we'll take them down. So we wrote those orders, and that was pretty good. We also got a couple of buildings repaired. Landlord said, I'm planning on repairing the building. I'm not planning on repairing it now. And we said, well, that's not going to work for us. You got to get into it now. Okay, so then we had 5 training sessions for engineers and inspectors. That was good. We trained our own guys. We went back yesterday and last week to see how many repair packages are in. 20. After we told landlords to fix their buildings, only 20 of them filed anything. Okay, so what have we got? They're scant on details. Let's talk about engineering calculations now. These things are scant on details. And our statutory requirements, they're broad. We're working on a building code to cover these things. The prescriptive 19th century codes, they were basically architectural layout codes. Didn't deal too much with the engineering aspect of them. And they had progressive collapse mechanisms built in, and they had high factors of safety. That is why these buildings have lasted. They are just chewing through these high factors of safety. And template existing drawings were not provided in the codes, and you can't get existing buildings as built. I've gone back through Tread Gold, I've gone back through Kidder Parker, I've gone back to all of these building codes from the 1850s. There's very little in there about how these things were assembled. Okay, so we're going to throw a couple of statutory requirements. Did these statutory requirements help you? Some of them do. So they're focused, but they're a little broad at the same time. This is 2014 statutory requirements, okay? The purpose of the New York construction is to provide reasonable minimum requirements and standards. That's a very interesting thing for existing buildings. The minimum requirements for existing buildings are very hard to come by. And that's why what happens is you get subject matter experts. What they do is they develop their own minimum standards in their office. I talked to a guy this morning, a principal of an engineering office this morning. They have their own standards for 19th century buildings because we have not established the numbers yet and the outer tolerances and the deformation thresholds. We're working on it, but we aren't there yet. The original 19th century codes, they were geometry-based codes. All walls should be 12 inches. All floors and joists should be strapped together. This, that, and the other. Don't forget to put a relieving wall around the stairwell. These, you know what these are? These are really high factors of safety, progressive collapse mechanism. If you actually engineer the buildings and you run the numbers backwards, they're not compatible with a factor of safety of 6. You actually find out that these buildings have a lot of capacity in them. There's a lot of retrievable capacity. What happens is they were all designed to be plumb straight and true. As they deform, that's where a lot of these things and the materials decay. That's where a lot of the factors of safety are getting chewed through. So what happens is you get a building that looks like it was in 1850, but it's actually deformed. And when it deforms, it's blowing through all of those factors of safety and hitting these very low stability thresholds. And the engineers are mixing that up. They think, okay, this building looks like it's been here for 150 years. They're missing the fact that the decay of the material has taken 50% of the factor of safety out of it. And the other issue is it's deformed to such an extent that you don't have a plumb, straight, and true gravity building. It's actually got a lateral component into this thing, which is lateral and slenderness ratio is the kiss of death for existing buildings. The second provision in there is our boilerplate that says all buildings and parts thereof have to be maintained safe. It's a great statement for us, but it's very broad because it's difficult to daisy chain and find out the specifications that went with that safe statement. Okay, here's one thing that you got to watch. Our participants today, owners and engineers immediately report unsafe condition. That's not negotiable, because if you go out there and you see a building that's not negotiable for us, we were lucky with one of those collapses, actually two of those collapses I showed you today, because we just happened to get a call in 2007 on the building on that old law tenement in Harlem, that we got a call from an engineer, an anonymous call, to say the building looked like it was going to collapse, and it was an anonymous call. And the engineer that was working for the developer next door gave us a call and said, this thing doesn't look. We were walking up to the building. One of my colleagues was walking to the building to check it when it collapsed in front of him. And that's happened to me. It happened to me on the building in the West Village where the chimney collapsed. I was inside the building doing an assessment. When I came out, the building let loose. Okay, so we have to get calls from our colleagues in the industry. A big takeaway today is call it in. If it doesn't look safe, call it in, so somebody gets an opportunity to look at this. I do not want this situation. That is unacceptable to me, because there is another engineer knocking around on this building and they never called it in. They said, well, I'm working on a set of drawings. The developer may do something. And I said, yeah, but I was at that building myself and it's unsafe. And he said, yeah, well, I thought, you know, we get another couple of months before I have to call it in. And that's a problem for me. Okay, and it'll be a problem for you too if that happens, if one of these things collapse. Here's the one. This is a building code requirement now that says building structures and parts of shall be designed and constructed in accordance with strength, design, load, and resistance factors, allowable stress, empirical and conventional construction. These buildings do not conform to elastic theory. So if you're using elastic theory, where you're expecting like steel and concrete, where you get a bit of recoil in the structure, where you can correlate deformation and stress, deformation and stress, these buildings will not conform to that. So you have to be careful of the analytical tools you're using. You know, you can use any of the general engineering principles, and they'll work, but you try and conform these buildings to deformation, you'll have trouble with this. A lot of engineers get tripped up in this. They run it through their engineering programs and the deformation knocks everybody's calculations out. Buildings can deform and still be very strong as long as they're plumb straight and true. And they were overbuilt to start with. The kiss of death for these buildings is lateral deformations. If they start to lean, you get these out of plane movements on the walls, and that's very difficult for these buildings to overcome. The transfer on the second floor is also instrumental in these buildings letting loose. Okay, so that's a big one. We've got to keep an eye on. Here's some of the 19th century codes. Okay, this is useful for us to know. Codes did not specifically identify corner lot buildings. Our code doesn't specify them now, and the codes from the 1800s never called it out, saying, by the way, if you've got a corner lot building, keep an eye on it because you'll have a soft story. Not in the code now, wasn't in the code way back when. The original 19th century codes had absolute requirements for walls to be plumb straight and true. That was never negotiable. So if you've got a leaning building or a buckle in the wall, that was an absolute in the code. That was the most serious structural issues at large and frequently incorrectly assessed. This is the one we have the most amount of trouble, where a building is not plumb straight and true. If you have a lateral component in these walls, they have to be tied to the floors. What happens is they pull free from the floors. The mechanical ties in an end wall building and the mechanical ties, the original mechanical ties in a corner lot building, they were virtually never included. Why? Because the builders didn't want to see the T-bars sticking out of the walls in the architectural walls facing the avenues and streets. Interestingly, in the blind wall that's left on the other side of the site, you'll usually see the tie bars in there because they'll be sticking out of the wall on the other side on the daylighting face of the wall. On the street and avenue side, they didn't put the T-bar sticking out of the wall, so they left them out entirely. So, but contemporary codes, we've sort of tackled that. That's, you know, plumbness and contemporary. So you'll find some compatibility in the code now for that. Running bond walls. Running bond walls are not easy to get them stable. Delamination and outside white delamination in these buildings is a serious issue. These red bricked, tuck pointed walls peel away from the backup 8-inch walls frequently. And they used what's called diagonal headers, the most rotten detail ever developed, to tie the face brick to the backup wall. And it was in the code. You know why it worked? It worked because they got some adhesion between the front and backup wall because of the mortar snots. The lime mortar snots adhered the layers together. And these mechanical ties, these diagonal headers, which were tucked into the back of broken bricks, they kind of worked when the walls were plumb straight and true. But when the wall buildings tipped a little bit, you get some outside load on the outside white. And that what happens is it comes away as a sheet. And that sheet is very frequently overlooked on these buildings. And the engineers miss it constantly. Okay, so that's that. Codes did not specify robust and sturdy connections. That's big in the New York City code now. And can any type of IBC code, you'll have a lot in there about connecting steel to steel, steel to concrete, concrete to concrete, wood to steel. But in these old connections, everything worked on gravity. And for a gravity system, they still kind of work because the gravity loads and the size of the walls will accommodate that type of load. But you'll find that as the buildings become out of plane, that positive connection, the robust connection between the floors and the walls is greatly diminished. So what stops the floors from going? Usually the relieving walls around the stairwell. But that's not the case in the soft story building. A soft story building is a real challenge because everything transfers at 2. Soft story buildings it's you know what they're called now? Designers call them transfer floors. So a soft story building, you know what that is? That's a transfer floor. So they're sort of interesting things to keep an eye on. And we've given good indications and we've shown you some engineering stuff. And it's not random. We can find these things. Watch these free wall buildings, unrestrained corner lots. If you're developing a site next door to them, they perform badly. And don't be caught in this dilemma where you didn't call in an unsafe condition. Call it in. Let's go out. Let's have a talk with the owners. Sometimes the owners don't know. And God forbid we have one of these things. It's not where we want to be, having one of these things let loose on a busy street or avenue. It's just not, we just don't want that. We don't want the injuries. We don't want the disruption to buildings. God forbid we don't want fatalities. Okay, and here's some code stuff, the original code stuff. I provided it. Manhattan in 1887, party walls 12 inches. Do you need a 12-inch party wall? Run the numbers on a 12-inch party wall. You only need 8 inches for 4 or 5-story buildings. Why did they have 12 inches? Because they're more stable if you lose the floor. Floor strength in 1860. This was a wonderful statement. In every building, the floor should be of sufficient strength to bear the weight imposed upon them. But it didn't tell you what the strength was. In the 1880s, it did. Okay, I get that. So how do you know that you've got sufficient strength to bear the weight upon them? That number was missing in the 1860s building code. Okay? But what it did say is don't overload it, and it should be the risk of the occupants, whether it's the same be owner or not. You know what they did is they put an enforcement statement in there. They said, here's an enforcement statement. Don't overload the floor. If you overload the floor, I've got a provision in the code to get you now. And by the way, the 12-inch walls, nearly every one of those dwelling houses I go to have 12-inch walls. There was 12-inch walls throughout Manhattan and Brooklyn all through the 1850s and 1860s and 1870s. Very rare to get an 8-inch wall there. And they're quite stable unless they bend. Walls plumb. This is a big one. That was an absolute statement. There was the 1860s Manhattan Code. All walls have to be plumb straight and true. Non-negotiable. Says it there. Shall be constructed of stone, brick, or iron. In Manhattan, non-combustible construction. This was the fire code, really. In 1860, wood frame construction was not allowed to be built, only outside the fire districts. And all walls had to be plumb straight and true. You know why? Because it's hard to make a plumb straight and true wall fall down. Okay, and here's an interesting one. 1882, calculations of floor based on factor safety at 3. That's a good number to go. So you can reverse that number of factor safety. That's really, it's a multiple to rupture number. And columns on vertical supports factor safety of 6. So these guys were thinking of factors of safety. And they were thinking of loads on floors. But a lot of the stuff was based on the geometry from fire. And that's why if you run the numbers backwards from factors of safety and factors of columns, you don't end up with the same member sizes in the building. Okay, so we've done a little bit of masonry erection and tolerances. We've given a little bit of prescriptive stuff. This was prescriptive in the code. But if you actually look at it, you know what these are? These are educational statements. You know, it's not really a specification in the modern sense of the word. These are like, these are descriptions of prescriptive buildings where the geometry of stuff is stated. It tells you wall thicknesses, gives you some dimensions, but it doesn't really give you stress values. It doesn't give you floor loads. These were sort of narrative statements. They're educational statements. They're statutes, but they're really educational statements. Okay, useful. Okay, so here's calculating load and stresses in walls. Original buildings, it's hard to contend with these out of plumb and buckled walls. So if they're out of plane, keep an eye on them and call them in and make sure they're not moving around. And floors were supposed to be tied together. End walls, corner lot buildings, this is a challenge. Deformations. Deformations were understood, but they were accommodated. There's virtually nothing in any of the codes about deformation. It turns up a little bit in foundations. It certainly says nothing about it in masonry, and it says nothing about it for floor joists. Okay, so you got to watch that deformation and the engineering calculation you're using. Our codes, they focus on alterations. Doesn't really say much about the evaluation for an existing building. We're going to have that eventually when we have the code, the new existing building codes. And you got to watch this issue. Walls buckle outwards. It's amazing. When walls buckle outwards, you have these fish mouthing of the walls. The joints open up. So instead of being 12 inches, it's a 6-inch wall. But you'll find that that load, that compression load, can easily be handled by 6 inches. So you have a wall that's 12-inch wall. It's got 10 pounds per square inch on it. All of a sudden, 6 inches is now it's buckled out of plane. So you get rid of the 6 inches because that's not taking any load. So all of the 10 pounds per square inch is on the 6 inches on the inside that's still in contact. That thing can easily accommodate twice that load, the original load of the building. So the original load of the building is not compatible with a factor of safety of 6. They were under stressed. So now you can double the load on the 6 inches of wall. So people are thinking, oh, the thing hasn't fallen down. They don't realize that every time the wall buckles, it's actually surcharging the remnant section of the wall that's left in contact. So what actually happens is you get this elongation of the wall, and that's what's really is happening is you have a KL over or an Euler problem where you get buckling of the wall and it's releasing from the floor. So they're not 10-foot walls. These walls actually, as they buckle, they turn into 20-foot walls where the compression load is only increased marginally, but you get this slenderness ratio as it's releasing from the floors. So we're watching that, and that's why we think that our calculations, we're kind of getting there with the calculations into it. Okay, watch that as these buildings, the safety factors are getting eaten up with deformation. They get eaten up through, how do factors of safety get eaten up? Overloading. You don't really get overloading in these buildings. It's just not true that people say things get overloaded. They're not really getting overloaded. What they're doing is the materials are deforming, and they're getting a lateral component, so they're not in gravity anymore. there's a big lateral component to the wall. That's a problem. And the other issue is the slenderness ratio for the wall's a problem. Okay, so contemporary codes don't really get there, and we're not there with that issue yet in the existing codes. Watch out of plane movement. Engineering design, you got to watch the end walls. Watch with sketches, we don't have them.